Hi, this is the lesson summary for lesson 3.3, which we did on November 19th and 20th. It's about finding the area of a circular annulus. You have to be careful the way you say that word, annulus. It's just a fancy word for a flat donut. Okay, so it's really easy to understand. You remember that the area of a circle is pi times the radius to the second power, pi r squared. Well, an annulus is a donut, right? So we've kind of punched a circle out of the middle of it. So in order to find the area of the annulus, really we just have to find the area of the big circle, whatever that is, and then we subtract the area of the smaller circle, the part that's not shaded in. So we're going to use a lowercase r to be the radius of the smaller circle, and an uppercase r to be the radius of the larger circle. And so you can imagine if I wanted to find the area of the larger circle, I would just do pi times the radius of the larger circle squared. And so that's why I used an uppercase r there. And if I wanted to find the area of the smaller circle, I would do pi times the radius of the smaller circle squared. So, I use the lowercase r there. It's just as simple as finding the area of the large circle and subtracting the area of the smaller circle. But there is one thing that I want to do to make this a little bit easier to use. Every time I multiply by the number pi is an irrational number, which means that it's an infinite, non-repeating random decimal. So no matter what I do, I always have to round my answers. And rounding is tricky because the more you round, the farther off you get. So I don't like having pi show up twice in the same formula. So what I'm going to do instead is I'm going to factor the pi out. Now, to remember how that works, remember algebra when we learned about like 2x plus 6? Take that expression. If you divide both of these terms by 2, that would be x plus 3. And so what I did was I factored the number 2 out of each of those expressions. If I were to come back and use the distributive property, 2 times x is 2x, 2 times 3 is 6, I just divided both of those terms by a common factor. And that is actually something we can do here because both of these terms have a common factor, the number pi, that pesky irrational number. So I'm going to divide both of these terms by a pi, put it in front of the parentheses, and then I can just see that it's just going to be pi times the difference of the squares of the radii. So the big radius squared minus the little radius squared. And I'm going to use that to do to find the area of any donut shape. I just take the big radius, square it, subtract the little radius and square it, and then multiply that answer by pi. So I have a couple examples that I want to go through. And it looks like I forgot to erase some of it, but that's okay. I'm just going to leave it there. So look at this first example. We did this in class. The outer radius, the big radius, is 10 centimeters from here to here. Okay, and then the inner radius is 8 centimeters from there to there. So if I just use the formula as I wrote it here, pi times the big radius squared minus the little radius squared, right? I'm just going to be finding the difference of the two areas. So pi times 10 squared minus 8 squared, which is pi times 100 minus 64, 10 times 10 and 8 times 8. Which is, 100 take away 64 is 36. And so the area, I can express it as just this one expression in terms of pi, 36 pi. And if I use a calculator and do 36 times 3.14, I think I get 113.04 square centimeters. Okay, that's the area of this entire donut all the way around. Okay, I did the big radius minus the little radius. For this other problem, which is a little bit more complex, this 9 centimeters is just the distance from here to here. So in other words, the inner radius is 9 centimeters. And then I also gave in this example that the width of the annulus is 3 centimeters, but that makes the outer radius actually 12 centimeters, 9 plus 3, right? So the outer radius is 12 centimeters. And so you could find the area of the annulus here because the area of the annulus would be pi times 12 squared minus 9 squared. But I got a little trickier because what I did was I said, let's not find the whole annulus. Let's find some fraction of that annulus. right? And so that fraction, remember that if we want to have a fraction of a circle, we can model that fraction by using this central angle over 360 degrees total, because that's, of course, the entire rotation. So I can multiply this. This is the area of the annulus. I can just multiply it by the fraction of the circle that's actually shaded in. And then you just have to be able to chug through on a calculator. And so the part that I didn't erase down here, I reduced 135 over 360. That reduces to 3/8. And then, of course, 12 to the second power is 144, and 9 to the second power is 81. So 144 take away 81 is 63 times pi, 63 pi. That's this part. And then if you just use your calculator and do 3/8 times 63 times pi, you get that number. So if you haven't had a chance, you should go to the GeoGebra investigation that I've posted and try the problems 1, 2, 3, and 4 at the end and see if you can find those shaded areas. And I'll see you next time.